Okay, let's start. So we are done with the lecture material. So kind of the intent for today, and I might hold another session on Friday evening, 6 to 8. I have a room reserved, but depending upon how today goes and how active you guys are, if there are no questions or not many questions, then I'll assume you're all set for the finals, and we will not do the Friday session. But if so, the other thing is just a reminder. So as I had said earlier on in the course, final is a 2 hour final, and the focus will be primarily on the post midterm material. But of course, you need to know combinational design to be able to do sequential design. As usual, cheat sheet, 8.5 by 11, two-sided. You can write in microscopic writing if you wish. You shouldn't need calculators. I would strongly recommend that you go through the act of making the cheat sheet yourself, because that's kind of the learning experience, really. Okay, just simply borrowing or copying your friend's cheat sheet, then you kind of miss out. You'll not know what's happening there. So question. Computer generated, okay? Yes, you can. Like I said, you can write it in 7-point font size, and I don't care. But that's all you're allowed. And again, as with rest of the it would basically be like the midterm in terms of I'll give you the sheets, you're going to answer there, so don't bring anything. So the exam slot officially sanctioned is a 3 hour slot, so the 2 hour exam would be at the beginning of that. So I think it's 11:30 to 2:30 is the slot. I don't know which room is, probably this one. So the final. So as far as sort of the time, the 2 hour time is going to be 11:30 to 1:30. Okay, so the beginning part of the exam, and also if you submit the design homework, the final design homework, then your weight essentially, or let me put it another way, if you do not submit the optional design homework, then the grade for that design homework would basically be prorated from your final grade, so final exams grade. So that's how it's going to work. Okay, so what I'm going to do is go through some random materials, basically same review I had done last time. I'll also go through uh, the PSET number 3, its solutions, which I'm going to hand out. Unfortunately, it doesn't seem like grader will be done with your particular like graded things in time for the final. So I'm going to walk through the solution that we have done. Okay. Question. Yeah, so it's a 2 hour exam. And all I was stating was that the 2 hours will be the first 2 hours of the official 3 hour slot. Right? So the office, like when you look at registrar office, it says the exam is 11:30 to 2:30. Our exam will be 2 hour, and it will be from 11:30 to 1:30. And any of you who have arrangements with um, Office of Disability and all, then your extra time is going to be after the exam. Okay, so just wanted to mention that. Okay, so before I start, any other questions? Okay, so questions from Piazza. I think someone asked these bunch of questions, and I thought they were kind of a little bit too long for me to attempt writing on Piazza. So hopefully the person is here. So let's go through some of these, and in fact, I'm going to turn them around and kind of ask everyone. So first question was, if a FSM has a small number of states, we can draw a state diagram. But if it has a very large number of states, finite number of states, do we draw a table or some sort of function? State functions were talked about, but my notes are not very clear. Okay, so what are the alternative ways we can represent functionality of a finite state system, finite state sequential system? So one is the state diagram. What else have we seen? The truth or state transition slash output tables, which are kind of an grandiose form of truth table. Okay, so that's second. And what's the third? Is there a third? Huh? Data path. So for data path, the way we do it is we again write the next state function and the output function, but we wrote it in that kind of a pseudocode type fashion. Okay, and of course, as a fourth one, you can write Boolean expressions corresponding to the next state and the output functions. Now, of course, um, uh, sort of it defeats the purpose if you're writing them at a very low level. So the advantage of finite state the diagrams and the pseudocode is that they are hopefully at a higher level, okay, as opposed to if I just were to throw a huge table at you or Boolean equations at you. So usually when we design, we kind of start at the higher level. Now, I think by the time, I mean, we have seen plenty of problems, and by the time you start hitting, let's say, maybe around 14, 15 states or something like that, and then after that, drawing becomes painful. State diagrams are kind of painful. So that's probably the limit, at least insofar as in a class setting is concerned. Of course, in real life, state machines can have hundreds of states, and people do make them. And one of the ways they make them is much like we do it in software. So how do we cope with the fact that our software can be very huge? How do we, what, like, I mean, if how do we reduce the complexity of writing software? Break it down into functions or methods, right? And then you call one function from another function, right? That's how we break them down. And the same thing you can do with state machines. So you can make hierarchical state machine. The idea is at the top level you have a state machine, and then one of the state in itself is a state machine. You pop one level deeper, and so on and so forth. So that can be done. I didn't discuss that in the class. So in sort of more professional settings and all, you have these hierarchical state machines which kind of are used to make things a bit more manageable. But again, as far as what we have seen in this class, we have only seen flat state diagrams. Okay, so what is one's pain threshold in terms of switching from diagrams to tables or pseudocode kind of depends. So I guess the very broad rule I said was things which are very data path oriented, as in you're manipulating many n-bit entities. Then the pseudocode type approach we use for data path is a natural. And likewise, on the other hand, when we're dealing with complicated things, but the input output are just single bit stuff. If you recall, in the P set number 3, we had I had those series of FSMs at the end, which were kind of rather complicated, and those of you who sort of attempted them successfully would had many states and a lot of edges and all going around. Pseudocode approach doesn't really work out there. So that's where the visual representation of state diagram kind of helps you out. So it's a qualitative answer to this one. We also talked about data paths. If we represent an FSM as a data path, do we draw a state function or sketch the circuit itself? So in some senses, sketching the circuit itself defeats the purpose of having any sort of high-level description. Now, having said that, for very simple stuff, it makes sense. Okay, you can certainly do that because we already saw some sequential building blocks. We saw counters and timers and these kind of things. So sometimes kind of the best representation or best specification of a sequential system is the system itself, okay, because it's so simple. But generally speaking, you would probably have to create that pseudocode kind of description. And so again, there's probably some sort of a complexity thing that this dictates that, yeah.
I guess the question is referencing to like the homework it asks for a schematic of the state function. Or
schematic of a state function? I don't think so.
It asks for the schematic of the data path or something.
Right, schematic of the data path is that wiring diagram. Modules connected to each other. Okay. So registers, adders, counters, timers, those kind of things.
Essentially, you would just build the circuit.
Essentially, you just build the circuit, yeah. But at a more abstract level, in the sense that you can use an n-bit adder, you can use an n-bit counter. You don't have to decompose it down to gates and all. Okay. So, yeah. What is a state vector approach? Is that a table or something else? So actually, I never taught state vector approach, but I think, Paul, you covered that in the class, right? Yeah. And Salma, did you also cover it? Okay. Yeah. So I'm going to go over that and just kind of tell you what its weaknesses are and why I did not cover it. Okay. So Let me open up a blank page. And now that I'm covering it, so you're supposed to know it. Okay. And I think I had explained this thing to a couple of students that come to my office hours. I guess my pet peeve this quarter was very few of you came to my office hours. It gave me plenty of free time, but still, as someone pointed out on Piazza, my office hours were always empty. But anyway, let's take a shot. State vector approach is kind of a way of approaching sequential systems where essentially you kind of shortcut all this high level stuff and all, but it comes with limitations and it's applicable only to certain kind of problems and it is inefficient. Okay, having said that, it's a quick and dirty design and it corresponds to roughly what you do in software. So let's take an example. Recall we had these kind of problems where I was saying I have a string of symbols coming in and I'm looking for a pattern in it, right? So I have letters coming in and I'm looking for AAPL or GOOG, those kind of things, right? We had those kind of problems. So the UCLA one, which I had in the lecture. And I had gone through, and in the homework, you had to do the FSMs and all. But there's a trivial, dirtier way, quick and dirty way of doing it. So let's take the example. Let's say I'm looking for UCLA in the string, okay? And I have a bunch of characters coming in, and let's keep the problem simple. I'm looking for successive appearance, like UCLA are the adjacent characters, okay? Now, one way directly I can kind of build this system is the following. My data is coming in, and it is ASCII. How many bits are in ASCII? 7, right? So 6:0 is a multi-bit signal. 7-bit signal coming in. Let's imagine that I feed them into a chain of 7-bit registers. Okay, so these are 7-bit registers running on a common clock. So this is also 7, this is also 7, this is also 7. Okay, let's say I'm feeding it characters one by one. What do you think is the relationship between what I am seeing at this wire versus this wire versus this wire versus this wire? So let's call this, so over time, every successive clock cycle, X is taking some value, right? So let's imagine that at this point in time, I have the value which came on clock cycle number I. Okay, so let's say at this stage, remember what's going to happen is every clock tick, I'm going to be, whatever is here will move out here, and whatever was here would move to the next stage, and whatever was here will move to the next stage. So if at any time here I have at clock tick number I, then what do you think is going to be here? +1, right? It's going to be the future value. So this would be I +1. I +2, and this is what the system would see in the next final one, and this happens to be the current value, current time, right? So now imagine I'm feeding characters to this thing, and let's say somewhere UCLA did occur. So at some point in time, so let's say over time, first character was, I don't know, A, then came B. So this is the time dimension. Okay, so this came the first, then this, then U, then C, then L, then A, and then some other characters, right? They're going to come like this. So at some stage, what would happen is I would see U, C, L, A at these lines. And if I'm looking for a pattern out here, all I have to do is take these things and feed them into a whole bunch of comparators, 7-bit comparators. So I'm going to compare this thing against A. So these are 7-bit comparators, okay, or equality checkers, which are nothing but, if all I want to do is equality checker, what do I use? XOR gates, right? So it's a very simple implementation. So I'll feed L's pattern out here, I'll feed C's pattern out here, and I'll feed U's pattern out here. And now I have 4 things which are basically saying whether the A matched, L matched, C matched, and U matched, and then all of them have to be true. So I have a gigantic AND gate, and this says match. I'm done. Okay. So very simple. It's very intuitive. Okay. This is called the state vector approach, because what we are doing is we are taking our data, okay, and then essentially treating the data as state. Okay. So the different points in our chain correspond to different points in the history of data that arrived. Of course, if I had a bigger pattern, if I was trying to match a bigger expression, then I'll need a bigger chain. Okay. Now let's talk about it. So let's say, so how many state bits are there in this implementation? 21. There are 3 stages of 7 bits, right? So there are total of 21 registers. So there are 21 state bits in this system. If I were to ask you to make a state machine, FSM diagram for this problem, how many states do you think you will need? Start state, U, C, L, A, and a bunch of arrows. 4. So 2 bits. So what was 2 bits of states, 4 states, 2 bits worth of state, is now 21 bits of state, right? And this goes to the heart of the notion of state, right? I had defined state as the essential information for the system to be able to do its job, the essential information about history. Now, of course, keeping a log of everything that happened, all the input that arrived, is one way of maintaining things, but it's not necessary information. It's a lot of it is redundant. So here, what's happening is instead of keeping track of that, hey, I saw a U, I'm actually storing the letter U. Okay, and likewise C and likewise L and A. Whereas in the FSM, we do not record the letter, but record the occurrence of the letter, right? Because that's all we need to remember. We need to remember that 3 cycles ago we saw the letter U, not maintain that U all along. So, so it's called state vector because this is kind of like a vector, taking my data vector and mapping it to the state. But it's very inefficient, as you can see, but it's very intuitive. Okay, now this kind of corresponds to how we do things in software, right? I mean, if I were to ask you that write a method which I'm going to call many times and I'm going to feed you one letter at a time, then you're probably going to maintain it like this. You're probably going to maintain letter that I saw 3 time units ago, 2 time units ago, 1 time unit ago, and the current letter, right? You're going to maintain them in variables. In a computer, you have a lot of memory out there, okay? And that memory is already paid for and there, so you might as well use it. But when you are designing hardwired circuits, or when you are in the business of designing the computer, you've got to be efficient. So this is not very efficient. This is fine for software realization of FSMs, but when we are realizing them as digital logic, it's not very efficient, okay? But there are other advantages out here. So let's say I were to now remember there was that problem about in the homework about look out for the phrase stock ticker symbol AAPL and GOOG. Okay, and I don't know about you guys, but I'll show you what my state machine was, and it's messy. Okay. Okay. So this is what my realization looks like. I will be sending around the link to the solution. But basically what I did was from a start state, the top one is AAPL, the bottom one is GOOG, and there are things going all over. Like for example, after the second A, if I see a third A, then I kind of stick out here. So there are different special cases that we have to handle and all. Nice thing out here is that I have only 9 states, which means I can get away with 4 bits. Okay. Now, how would we do it with the state vector approach? Well, I showed you how we can make for a single thing. So now let's see. Given this, if I were to now say, okay, let's say you can use the state vector approach, and now you have to design that system of recognizing AAPL and recognizing GOG, whichever one is occurring. Okay, how would you do it?
You do the same thing you did with the end. So you still have the same 3 registers. You just have another set of comparators.
Mm-hmm.
Or
the 2. Okay, so I can, for every string I'm trying to match, I can create such a machine, and then after the AND gate, I can have an OR gate, right? That will solve the problem. Now, for our particular example, now I will need 42 bits of state, 21 for Apple, 21 for Google, 42, and that corresponds to 6. So we have 42 states versus whatever 9 states. Okay, so number of bits go up from 4 to 6 registers, right? So yeah, just going to need more. So sorry, am I screwing it up? So we have 21, 21, yeah, 42 versus 9, yeah. Okay, so
can you just use the same 3, but then
no. So by the way, I'm confusing things. Okay, so I have 42 state bits, which is 2 to the power 42 states. Okay, so this particular system has 21 state registers. Therefore, the number of states it has is 2 to the power 21. Okay, because I'm maintaining entire history of the previous 3 characters, so I have to worry about every possibility. So humongous saving, as you can see, by kind of going to the state diagram. You have a question?
Yeah, so if we keep for the Apple and Google one, can we still use the same 3 registers and the same 21 bits of state, but then just have a different comparator, another set of comparators just attached to the same spots?
Actually, you're right. You can do that in this case. So it would still be 21 bits. You're right. Yeah. So I can. Yeah. So I can maintain many of these. Okay. So I guess my length out here will be decided by the longest string I'm seeking to match. Okay. Good point. Yeah.
How can you tell so quickly how many states you have?
So number of state, so there are 2 different things. How many states and how many bits of state registers, right? So here each register is 7-bit. I have 3 of them, so 21 bits. That means my total number of states is 2 to the power 21. Now, in an actual running system, if I'm only receiving alphanumeric characters, not all of the bit patterns are being used, right? Because, for example, maybe ASCII code also has some control characters and all, which never occur in text. They will probably never occur, but that doesn't help me. I still have paid for these registers, okay? Whereas if I were to start with kind of the FSM diagram and then implement it with a compact coding, I can get away with just very few registers, okay? And how many of these I need means what is the oldest data that I'm dependent on, right? So if I am trying to match a whole paragraph, well, I'll have a paragraph worth of registers, which is insanely expensive. That's not how you're going to do it. In fact, that's not how you're going to do it even in software, right? I mean, it's one thing to say in software you're trying to write a function to match a small word, but if I were to ask you, you have to match, I don't know, like in Google, you can type entire sentences and it finds you the match, right? I mean, it certainly doesn't sort of literally store entire strings and does that matching. It actually also creates an FSM diagram, much like we do. In those of you in computer science, you'll probably at some stage do courses which are about compilers, where you actually take a program and compile it, and those compilers rely on finite state machines, and there are special tools which can take a description of what strings you want to recognize, something called regular expressions. Anyone heard of them? Okay, and from regular expressions they can generate a finite state machine diagram and then implement that FSM diagram in software. That's how matching is done in software. In fact, regular expressions and FSM are equivalent. exactly one and the same thing. Whatever regular expression can express, FSM can do, and vice versa. You can go back and forth. Okay, so anyway, so even in software for more complicated things, you have to do it this. Otherwise, the state blows up. You have to store a lot of data. Okay, is this sort of hopefully clear to everyone? That how we can do this thing. Now there are a lot of other. Now let's say I were to change this thing slightly. I were to say, I'm not looking for UCLA in successive thing. I'm looking for UCLA occurring in that order, but maybe separated by other characters. And now suddenly the problem has blown up. I cannot even implement it this way, right? Because UCLA may occur an infinitely number of characters apart. So it's impossible to implement it this way, even though it is an FSM system, right? Because I can create an FSM diagram. All we have to do is stay in a place if I'm seeing some other characters. So complexity of this thing blows up. The generality of this thing is very limited. So that was part of the reason I didn't sort of talk about it, because frankly, this works for simple toy problems, okay, and not kind of a general strategy to use. But on the other hand, for certain quick and dirty cases, it's probably a fine thing to use. So when I ask you to design an FSM and all, I actually do expect you to go through the FSM diagram and all, unless stated explicitly otherwise. So this way of doing things is generally not acceptable insofar as this class is concerned. Okay, let's go back. So state vector approach, is that a table or something else? Well, it's not a table. It's kind of just jumping straight to the schematic. Okay. When we talked about control FSMs and data paths, so is that like an ALU? What is an ALU? Anyone? Yeah. Yeah, it's largely a combinational thing. Okay, so FSM data path, I guess ALUs are used in data path, but they're not synonymous with data path. Usually, data path would have ALU together with registers and perhaps some other sequential stuff as well, and some other combinational stuff as well. FSM feeds microcode to the data path, micro instructions. So the connections going from control FSM to the data path are a set of bits which are basically telling data path what to do. And the data path in every clock cycle is sending some status information back. So we saw examples like the vending machine and stuff like that, which kind of were doing that. Or even the solution I had presented to the Morse code transmitter, I had very simple things like go and done. That was the interaction between the control side and the data path side.
There's a question about ALU.
Mm-hmm.
If you have like variable length, like I guess instructions you could do with ALU, like maybe multiplication takes 8 cycles and addition takes 2 cycles.
You just spin on it. So your control state machine controller is going to wait on it.
Wait
until a done signal. So in fact, for the current design assignment, you would need to do something like that, because I limited the number of adders you can use. So you cannot just construct a combinational multiplier. Okay. So, okay. And the data path has a lot of complex circuitry. Is that correct or something totally different? Yeah, intuitive, roughly speaking, right? So most complicated designs are going to look like data path, which is handling kind of multi-bit stuff, and a controller, which is handling kind of complex flow of logic, the sequencing of the data path. So that's kind of what ends up happening. Another thing I wanted to point out was the following. If you look at a finite state machine, FSM diagram, if you may, at any point in time, it is in a single state, right? It's every clock tick. It looks at the input, it decides what the next state is, and the next state is, and right. But at any given point in time, it is in a single state, which is kind of like our sequential program. So when you write software, kind of the simplest notion of program is my function, I start running, one statement, for next statement, and all. But then our computers do stuff in parallel. We can run multiple programs, and those multiple programs can talk to each other. We can have multiple parallel things running even within a single program. What are they called? Anyone? Threads, right? So I can have multi-threaded programs. Likewise, you can imagine systems which have multiple FSMs. and they talk to each other. Control data path is one example of it, right? Each one of them is running independently, and one machine's output is the other machine's input, and vice versa. So that was a very simple example of two FSMs running in parallel. It just so happened that one was designed using one we were calling as control, the other we were calling as data path. But generally speaking, you can imagine I can have multiple FSMs, many hundreds, and they are talking to each other. One of them sends a signal to another one, and so on and so forth. In fact, most complicated systems are kind of like that. Let's take something like the following. Networks or computer networks, they use protocols to talk to each other, right? Anyone knows what those protocols are called?
Well, I mean, you have like the OIS layer system. So
Right, OSI layers.
you have like physical, and then above that you have like Ethernet and then TCP/IP.
Okay, TCP/IP. So TCP/IP is the bread and butter of internet networks, right? TCP is basically a very grandiose, complex protocol for computers to handshake with each other, send data to each other, slow down if the network is congested and all. And TCP is actually nothing but a very complicated FSM. Okay, on each computer is running the TCP FSM, and what's happening is the output of one computer, which are basically data packets, go to the other computer and they act as input to the TCP on that side, and vice versa. So our internet is nothing but an assemblage of billions of TCP state machines talking with each other. Okay, and it's probably the most complicated, one of the most complicated system that you can imagine. So what ends up happening in many of these systems then is, let me open another blank page, I guess. That I can have many FSMs so I can have many FSMs, FSM1, FSM2, and they can talk to each other. So like this guy's output may be FSM, and this may send some signals. This may send signals out here, and each one of them are running in parallel. Okay, FSM1 could be in some state, FSM2 could be in some other state, FSM3 could be in some other state, and so on and so forth. Okay, so each one of these is some state machine. Okay, likewise something is happening out here. Okay, some junk. Okay, and so on and so forth. Each has an independent, that's very important, FSM. Each is an independent FSM. Okay, so let's imagine that this FSM can be in n1 possible states. This FSM has n2 possible states, and this one has n sub n possible states. If I look at the overall system, all possibilities may occur. This guy may be in one of the n1 states, this guy could be in any one of the n2 states, this guy could be in any one of the nn states. So the overall system has the number of states it can be in is the product of all of them, right? So let's imagine I take two state machines. One of them could be in one of two possible states and the other could be in one of two possible states. I'll look at the combination. The overall thing could be any of the four possible states. The four possible states would be machine 1 being in state 1 and machine 2 being in state 1. The second state would be machine 1 being in state 1, machine 2 being in state 2, and so on and so forth. The reason we do it this way is that, so let's take a very simple example. Let's say I have two FSM. FSM1 has 10 states, and let's say FSM2 has 10 states. Then the total system will have 100 states. Instead of designing a system with 100 states, I'm going to design two systems with 10 states and have them talk to each other. A lot simpler design, as long as I can keep track of how they're interacting with each other. This is why parallel programming is useful, and this is why hardware parallelism is useful. You break things down into simpler, more manageable kind of pieces. So oftentimes in system design, in digital system design, we end up taking this route, and the idea is you take stuff which is logically independent and keep them separate. So control data path was one example, but many other situations may happen. Let's take an example. Let's say television. Okay, yeah, the television. So many things happen on television, right? On one hand, it has to receive the signals, decode it. Nowadays, televisions are very smart. They connect to the internet, so they probably have a TCP state machine. They have all sort of other stuff going on. On the other hand, they also have to look for our remote button presses or pressing the switch, the whole user interaction part. And these are kind of logically independent for the most part. They kind of interact somehow deeper down, but what's happening is that these systems simultaneously are coping with a lot of different things, a lot of different inputs and outputs. Or like take our car. Our car has infotainment systems where sort of radio buttons and stuff like that. It is coping with sensor inputs from the wheels and all. It is nowadays they also have radars and these kind of things to kind of uh, blind spot detection, these kind of things. So there's a whole bunch of input coming in. And instead of designing a single finite state machine to cope with everything and creating a monstrous stuff with gazillions of states, you create dedicated finite state machine for each one of these things. So you'll have a finite state machine for anti-log system. You'll have a finite state machine for I don't know detecting collision. Finite state machine for monitoring the inputs you are feeding to the AC and the radio and things like that. And all of these things deep down are interacting with each other, sending messages to each other, or talking to some sort of a data path. So many different FSMs could be designed and they're independently observing things. So let's take an example. One of the problems in the uh, okay, remember this problem, which basically was requiring you to so I had sensors X and Y. I had some sort of a input called Z, which was indicating a sensing session. And you were monitoring for two things. You were monitoring for number of ones on X during the session is equal to number of Ys during the session, and also this other thing. So there are two different things going on. Now this happens to be actually a bad example, but let's say for each one of these two, a finite state machine was possible. Then what I could do is design these things independently and then combine their output. Okay, so I could have designed it this way. The reason I say this is a bad example is because the first one by itself, number of ones during a session is equal to number of ones on Y during the session, is actually not an FSM problem. Okay, the whole thing is an FSM, but this one is not. Okay, this just by itself. But many other times that the situation may be that you are doing multiple things. You may be doing a pattern checking on the string on incoming things and perhaps doing some other task also, and you combine them. So sometimes breaking a complicated system into individual pieces becomes important or becomes essential. We saw a little bit of that in the Morse code example. Okay, we had, I mean, if you look at the overall system, we have a control FSM for the transmitter, a control FSM for the receiver, but even on the even on the transmitter side, you could imagine breaking your FSM into something which is interacting with the keyboard, something which was interacting with the wire. So you divide and conquer kind of approach. Not everything has to be shoehorned into a single FSM. Break it down, make it simpler. Same thing in combinational. We see, but sequential is harder. So, okay. Any questions before I move on to? Yeah.
So why is your FSM so complicated for this? Like, so the way that I did this one was essentially like I built states so that like I would give say like Y positive values and X negative values. So if you for now ignore the ready states and outputs or whatever. So essentially, if it's a Y, then it goes positive, and then if it's left, it goes.
Okay, so I think firstly the previous original problem is this. Okay,
Right.
So this is simple. What's happening? So again, I think this is a good instructive example for an FSM. So I have a system, two 1-bit inputs x and y, which correspond to inputs from two sensors. So these sensors are monitoring some sort of a target, and the target can occur in two types. It could be the X type and could be the Y type. Okay. So what's happening at any time instant, there are three possibilities. Neither sensor is reporting anything, or X sensor is reporting something, or the Y sensor is reporting something. Okay. And the case that both sensors are reporting is not possible because the target cannot be both types. So that's a don't care for us. So, and what we want to do is we want to make sure that the number of type 1 events since the system started and the number of type 2 events since the system started are the difference between them is 2 or less. Okay, so the way you can imagine doing it is I start out, nothing has arrived, so I'm in the equality state, and every time type X event happens, I move to the right, and every time type Y event happens, I move to the left, except that if I see more than two successive from this state, so I move on X out here, move on X out here, and now if I again see an X, I basically go to an error state and then stay put there, and likewise on Y. So essentially what's happening is I'm kind of walking back and forth. As long as the system is meeting the guarantees, it would be in one of these 5 states. And the additional self loops correspond to saying no event arrived, and I took advantage of the don't care to just write X equal Y out here. You could do it differently if you wished. So if after starting I saw a Y, I would move out here. If an X came, I'll move back out here. That's what it is saying, not X and Y, okay, or X and not Y, okay. And if I ever sort of went more than two number of X minus number of Y or more than two separate, I will end up in this state and stay put there forever. Okay, so this was a simple case, and what it also shows is that even that this clearly is an FSM finite state problem. I didn't need to keep track of the entire log. Next problem became more complicated. Okay, so it's basically saying that as a part of the complexity is I introduced this notion of a session. So the idea is that there is a input called Z, which basically tells the system start sensing, and then at some stage it says stop sensing by going down. And what we are doing is basically at the end, when the session has ended, I want to set the output to either 1 or 0, depending upon whether the conditions were met or not. So the idea is if the two conditions were satisfied, one condition is the same as the previous problem, which is number of ones minus number of x's minus number of y was always within 2 of each other throughout the session. And the other one is that at the end of the session, the number of ones and number of x and number of y's were equal. Okay, these are the two conditions we have to check. Now, earlier I had a problem which was, if actually I go back a little bit, there was a problem which said the system has 1 bit input in and a 1 bit output y such that out equal to 1 if number of ones seen thus far, number of ones on in seen thus far is equal to number of zeros thus far. And this is not a finite state problem because I could have an arbitrary number of ones which could have arrived before even 0 began to arrive. So you could imagine that it's perfectly fine that a million ones may have arrived and then followed by a million y's, and then I have to output a 1. I cannot, so there's no bound on this thing. So going back out here, and actually I recall on Piazza there were some questions around that time where from this the extrapolation was made by some students that therefore it is not possible to do this problem, because one of the conditions out here is kind of that nature. My sensing session could be arbitrarily large, but that is not true. Okay, so now further thing is that when the session ends, what this problem says is for one cycle only, you have to make the proper output, out equal to 1 and ready equal to 1, or out equal to 0 and ready equal to 1. At all other times, ready is 0 and out is 0. So the way I approach this problem, and it's basically kind of doing the same thing, I started with the following intuition. I said, look, what kind of patterns are acceptable? Okay, and basically there are two kind of patterns which are acceptable. Okay, and let me this kind of thing is called as a regular expression, and what it is saying is the following. So star means 0 or more of the previous thing. And this is the OR symbol. So this is saying that any pattern which is of the form that I saw an X and then I saw 0 or more XY and then saw a Y is an acceptable pattern. As you can see in this pattern, at the end, number of X will be equal to number of Y, and the count of X and Y will never be more than 2 away. Yeah. And the other possibility is this one, Y followed by a whole bunch of YX followed by X. And in between, I may have stuff which are empty, right? No observation, nothing, okay? But if I am seeing an X or a Y, they must occur in either this sequence or this sequence. Anything else, I fail. And then I have to wrap around this thing all the other timing constraints. Go ahead.
Okay, so if we were to go to the previous one, previous page. So why would you not be able to use this FSM, but then essentially you would attach some other outputs? Because what you would be able to do is essentially say, when it's done, then it has to go from what is currently marked as 0.
No.
Why would that?
No. The reason it won't. Okay. So there are. So let's. It's possible that let's see. So at the end, okay. So what you're suggesting is take this thing, and if I have an end situation, then I kind of go out of this one.
Right.
Okay. So I'm roaming around in this thing. I never violated the condition that I will ever 2 away. So as long as I stayed put in these regimes, I'm meeting one condition. And I guess the second condition you are saying is the equality condition, which basically would translate into this guy. Yeah, you could probably approach it that way too. You'll still have to wrap around it, all the things. What happens if my session ends in any one of these stages?
Right. So you would do is only the middle one goes to your
success state. All the other ones will have to go into a wait state, time things out and do it. So essentially my system ends up doing the same thing. Okay. If you kind of so let me walk through it, what is happening out here. I start out in a start state. Left hand side corresponds to one pattern, the right hand side corresponds to the other pattern. So what's happening out here is I start out, I keep spinning out here if I have no session, or I am in sensing session and I'm getting neither X nor Y. Okay, so X equal to Y. I keep spinning out here. The moment it happens that I am in session, so Z is high, and I observe an X but not Y, I transition to this state, and then I keep going back and forth out here. X takes me here, Y takes me back, X takes me here, Y takes me back, and at the end, and then if I ever see a Y from this state, I come out from this side. So this is implementing this pattern X, X, Y, star, Y. On the left hand side, this guy is implementing the corresponding pattern Y, Y, star, X. So these 3 nodes are implementing that. So you can think of these as corresponding to kind of the 2 side lobes in the original design. And then what happens is there are a bunch of conditions out here. So let's look at, let's say, this guy. So I'm going to be here. That corresponds to that I have seen X, I have seen bunch of XY, and then I have seen an X. That's why I'm out here. And let's say the session ends while I'm in this state. If the session ends, if I'm that state, then it's a failure. So I have, if I'm in the state and the session ends, I see a not Z, I go to my failed state out here. Another possibility is I'm in this state, and instead of seeing a Y, I see another X. In which case, I again have to fail, but I don't fail immediately. I'm still in session. So I move to this state called wait, and I'm going to wait my time here, spinning on as long as the session is valid. And then when there is no session, I move back out here. And I'm doing the same thing on the left-hand side, just for the mirror situation. And all these other additional arrows are kind of basically taking care of session management, which is happening. So I would urge you to kind of look at these kind of things, how I kind of structured it. But I find it personally useful to kind of see what kind of patterns are acceptable. Okay, and in a more general form, I could, the simpler patterns we had things like UCLA, AAPL, those kind of things. But let's say I were to offer things like, you can have A and as many B as you want, C, a pattern like that, A, B star C. Okay, that so that will accept A, B, A, C, A, B, C, A, B, B, C, A, triple B, C, and so on and so forth. All of them are acceptable. The state vector approach cannot even begin to approach this thing. But thinking about the pattern, and then wherever you see kind of like I have a repeat, that basically means I have a self loop going on. So I like to think in that terms, but there are many other ways. So clearly, V2 came at sort of the problem from a different perspective. I thought differently out here. So there could be multiple correct approaches to approaching an FSM, and some may be more efficient than others. Okay. How many of you had this kind of a design on this problem? Pretty much everyone got it. Most of you. Okay. I think clearly kind of this last problem was much harder. Okay, but let's look at some others that we had done. So this I already showed. It's the Apple and Google one. So 2 examples. The way if I give you a fixed pattern, just string AAPL and all, the way I like to approach these things is I first draw the correct match. Let's imagine that I was lucky, and what is happening? So I start, I get an A, I get an A, I get a P, I get an L, and I just draw that out. And the other possibility is I'm starting and I get Google. Okay, in this case, the nice thing was these 2 patterns are totally disjoint. They're not sharing any character. So I draw something out for Google. And then I think about each one case, what arrows that we have to draw. Let's take an example. I'm in this, I moved to the first state. I saw an A, I'm in this state. What are the possibilities? Well, if I see an A, I move to S2. So that's the good case. If I'm here and I see a G, that means I should jump to the, could be a potential start of the Google pattern, so I jump out here. So what you see out of this state is 2 possibilities, A or G, and the remaining one, I see anything else, I go back to start. Likewise, I move to the next state. I think out here. So I have now seen 2 A's, A, and I'm sitting out here. If a P comes, I move to the next state. That's the correct case. If a G comes, I have to go to the start of Google pattern. So P and G. There's another possibility. Another A may come. So I may have something like APL. That should match. So for A, I self-spin, and everything else, I go back out here. And you play the same game with every state. So every state, you kind of think about all the possibilities and how will you react to that. Now, this issue was made more explicit in this trickier problem, which was COCOA. Now, this is a one which often people have a hard time getting right, and I wouldn't be surprised that if many of you haven't. So let's think about it, what's happening out here. So again, starting with my strategy of first draw out the correct case. So start state COCOA. I just draw that out. And in this particular case, and once I see this pattern, then I'm kind of done and have to do. Now let's think about every possibility. So I'm in the current state, and I think I did not draw this correctly. Should say something out here. So I'm in the start state, and if I see C, I should move to the next state. But if I'm not seeing C, so this should really say self. Okay, so as long as I'm not seeing a C, I stay put. The moment I see a C, I go out here. In this next state, I have a possibility that, so if I get O, that's the correct case. If I see a C, I should stay put out here because I could have something like C, 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 O, C, O, A. Okay, so I stay put out here. Anything else, I go back. So what you see out here is in not equal to C and in not equal to O. Next possibility out here. So I'm in the state, I have seen CO, start of the pattern. If I get a C, I move to the next state. That's a good case. If I see anything else, I go back because that's the only thing I can do. Next one, I have seen COC. If I get an O, I move to the next state. That's a correct case. If I see a C, then I may be in a situation where it's the start of another cocoa pattern. So when I see a C, I go back to the state S1, which marks that I have seen a C. And anything else, I go back to the start state. Finally, in this state, O, so I've seen now COCO. If I get an A, that's a good case. If I see a C, then what may be happening is that I may be seeing COCOCOCOCOA. Okay, so what I do is I go back out here. That's the tricky one. So basically, many students kind of miss out on this arrow or this arrow. These are the two arrows which students have kind of a hard time dealing with. So think sort of a little bit deeply out there. And then everything else I go back to the start state. And finally, if once I have matched a cocoa, if I see a C, that could be start of another cocoa, so I go back out here. Otherwise, I go back to the start state. So every state kind of just think through all possibilities. How should you react to it? Question.
With regards to the amount of states you have, is the last one necessary?
This state?
Yeah, the very last.
Because that's the only, the last one you know, right? Yeah, because that's the only place I can output a 1.
Yeah, what I'm saying, in case if you have like a new implementation and just say after I have COCO and I need I have an A.
Oh, so you are doing a melee and then you kind of jump back out here. Yeah, it's possible. Yeah, okay. Yeah, melee can be more efficient. So that's the other thing. Whether you pick melee or more is kind of the other decision. I tend to prefer melee more because I think they're generally simpler to reason about. But even though they cause a bit of a delay and all, and also in reality they're easier to implement robustly in hardware. So I just have a bias, but melee can certainly do the trick. So so let me think about it. So if I have an A, while seeing an A, I guess the issue for you would be the following. After seeing an A, where will you go to? Back to where you start, and then you wait for a C. Yeah, okay. Yeah. Yeah, you're looking for a placebo. Yeah, you could do that.
With regards to like the previous slide, we know we have to do like the A, P, I, G, O, G.
Uh-huh.
Now, I see that we have like a slightly different division why. Because in my case, I simply just divided I have like, if you want to look at it in the case of like 2 branches, like one I'm only looking for one pattern and the other I'm looking for the other. So say if I were to be at my initial and start and if I read an A and I branch to this other area, so I'm saying I'm looking for a pattern. And then if in your case S1, if I don't have an A,
if you, I guess in your case, what will you do if you get a G?
A G, I just have to go back.
Go back here. No, you have to go back out here. Going back out here would mean that you would miss the Google pattern. Yeah. Because if you are branching from out here, if I go back out here, then let's say I got the pattern AGOOG. Whereas if you go back out here, the only pattern you can accept is AGGOOG. Because the only way you'll transition out is with the second G.
You said the pattern you're talking about is AGOG?
Yeah.
Okay, so let's start out there and I have it.
So A, I move out here. So try to think of what these states mean. This state means I have not seen anything. This state means I have seen an A, and so it's a potential start of an apple. And this state means that I have seen a G, and it's a potential start of Google. So that's the other thing. I think if you give states names or at least have a mental map of what they stand for, okay, that kind of helps things also.
If you wanted to detect the substrings AAPG and GOOG.
Say it again.
AAPG.
Let me just write it down here. So AA, PG,
and GOOG.
Okay.
Like the acceptable that if you're along the top path where you're going, oh, I've seen an A, now I've seen AA.
Yeah, so what will happen? So you AAPG, the problem out here is what happens here. So if you see an O, you should jump to the state.
Okay, so then should I delay one clock cycle to ensure that the letter that comes after the G is not an O, so I can decide whether
No, don't have to delay anything. You make two branches, one for AAPG, the other is GOOG, and then for each one, for this state, you are in this state, you have seen a G, and what's the next character? Well, if the next character is an O, you should go out here because this state stands for I have seen a G.
Okay. But if you see a G after seeing AAP, you need to set success or out to 1, right?
Oh, okay. That's the other thing. How is a problem defined? Okay, so in this case, if I'm saying I'm detecting these, so if I'm doing AAPG, the moment I have seen G, okay, so that would be the equivalent of this state out here. Yeah. In this state, I will have a 1.
Right.
Okay, so that's indicating that I have seen AAPG, and then, but if in this state I see an O, I'll jump out here. Okay. So I would really urge you to look through the internet, find FSM problems. There are plenty of courses taught, lots of material floating around on the web. Try to solve them. Okay, I mean, I just cannot emphasize that, particularly if you're not comfortable with FSMs. Okay, it's very easy to get them wrong, and it's very easy to also get them very inefficient. And look, I won't pretend I get them wrong often. Okay, the first time I did the cocoa problem, I missed one of the edges also. Okay, so it's they can tax your brain a little bit. Okay, and the other thing is, unfortunately, there is no simple test to say whether something is solvable as an FSM or not. And what that also means, therefore, is that I am unlikely to give you a problem where I will ask you whether it is solvable by an FSM or not, unless it's very obvious that it cannot be done by an FSM. Okay, because proving something cannot be done by an FSM is very hard. Okay, in fact, I wouldn't be surprised if it is not possible. Okay, just bear with me. So therefore, if a problem is of modest complexity and I have given you to solve it, that means it can be done by an FSM. Okay, so don't waste your time thinking about, oh, it cannot be done. Okay, there are ways of systematically proving these things, but again, not easy, and they are not material to this class. So again, the only case out of this problem which was not solvable was an obvious one: number of ones and number of zeros. Okay, question.
I know you just said you're not going to cover, but like in that example, it was obvious because it would theoretically require infinite memory because it was unbounded. Is that a common characteristic that you see? Like, what makes it so difficult?
Yeah. So it's actually codified as a couple of theorems, and they're usually taught in the automata theory class in computer science. I don't know whether you're E or CS, but if you're CS, you'll probably be required to do that class. Okay. So there are systematic ways of kind of going around. Usually the way these, I mean, even there's not a mechanical recipe. You still have to apply your brain and kind of apply those theorems. So that theorems are a guidepost, but it doesn't mean I can write a program where you give a problem spec and I will apply it and show whether it's possible or not, at least to the best of my understanding. Okay, so try as many problems of FSM type as you can. You can just never try practice enough on this stuff. Okay, let's go back to so designing sequential circuits systematically. So roughly speaking, we have seen 3 kinds of problems, and that roughly corresponds to sort of what you can expect on the final. Okay, one class of problems which are forcing you to implement a sequential system all the way down to a reasonable level of detail. You are mapping it to a circuit. Another class of problem is where they're more complicated. I ask you to design an FSM, as in draw an FSM diagram, but we stop there. And a third one are even more complicated, where I give you a complicated sounding system description, and then I expect you to come up with data path together with the controller FSM as necessary. So this problem falls into the category which is kind of the first category. So circuit has one input W, has one output Z. All changes occur on the positive edge of the clock. Output Z equal to 1 if input was 1 during the 2 immediately preceding clock cycle. Okay. Now, so this is basically what it's showing, that if this is W, then Z is going to be, in this case, there is a 1-1 pattern out here. It will be 1 and 1 twice out here. Okay, now which type of problem does it fall into? If you think about it, it's kind of our pattern matching problem that we have been seeing. The pattern here happens to be 1-1. It's a sliding window case, as in after I see 1-1, then the next, I could also, if you see out here, this sequence of 3 1s is really 2 1s, two matches. There is a 1-1 match here, and then another 1-1 match out here. Okay. You could approach this thing with the state vector approach. In this particular case, that would sort of work fine. And in fact, since we are dealing with single bit signals, the state vector approach here would probably be equally efficient. Okay. So that would be the easiest one. So does someone want to give me the state vector based circuit for this? So yeah.
So you take in W.
Okay, so let me open a page and you can guide me through. Okay, so what do you want me to do?
You have your input W.
So are you firstly making the circuit or FSM diagram?
Circuit.
Circuit. Okay, so I have the input W.
And it goes into flip flop.
Goes into a flip flop.
Okay. And then you have something. So then you take the before the flip flop. And you XOR it with 1. You take after the flip flop and XOR it with 1. And then you AND those two.
Okay. So is this obvious, Terry, on what's happening?
Isn't the state the current time input, not the last?
Huh? Yeah, so there's a mini thing, so you'll have to add then. Okay, you're right. Okay, so I'm basically looking at, yeah, this is going to be both 1-1. Okay, so we can simplify further. But in a simple case like this, kind of you can directly jump to this thing unless I ask you to make an FSM diagram. Let's make an FSM diagram. So what would happen? I'm in a start state. This is my start state. What would I do? If I'm getting 0, I stay put. If I get 1, I move to another state. Now this is still not enough. I have to see a second one to be successful. Second one, I'm successful. So out equal to 1 here. Meanwhile, if I'm out here, I get a 0. Sorry. I get a 0, I go back. So I've covered those two cases. And here, if I get a 0, I go back. If I get a 1, I spin. Okay. The fact that in this particular case, the 1 was happening after the clock cycle is indicative it's a Moore machine. Okay, otherwise it would have happened in the same clock cycle. Okay, the difference is the effect on the output in case of Mealy is immediate, whereas in Moore is delayed by 1 clock cycle. So this is what we kind of end up with out here. Okay, is this clear to everyone? Different ways of approaching it. Simplest state, one or single thing. Okay, let's look at this. So, this is the state table, so I can write it as a state table. So for present states and kind of what's happening, then we give states some numbers. They're binary patterns. There is a don't care because we have 3 states. And yeah, question. This one? Oh, the one I drew? Yeah. wouldn't it output a 1? It's outputting 1 here. It's outputting 0 here. It's outputting. Yeah, it will output a 1 on the next clock tick. No, remember, it will make this transition when it sees a 1, right? So if you think of it this way, that at let's try to draw this thing, okay? What is happening with W? Let's imagine W is coming from similar clock synchronized fashion. Okay, so W, if it changes, is also changing on the clock edge only as a result of the clock edge. So as a result of some clock edge, W changes to 1, let's say. Okay, so I will observe this fact at this clock edge, and at that time I will move to the first state. And if it stayed 1, then at this edge, again I will observe that fact, right? So I'm observing the fact that input was 1 at the end, not at the beginning, because the input changes are themselves happening as a result of some clock edge. So I couldn't have observed the fact that input became 1 right at this clock edge, because it happened after the clock edge already. So now what happens is, at this clock edge, I will move to the final state and I'll begin to output 1. So my output is going to look like this. And at this stage, this guy can go down for all I care. That's what will happen. Okay. So think in terms of, I think the cleanest way of thinking about these systems is, and which is why, by the way, I also like the Moore machine, is that inputs are also changing in a clock synchronized fashion. When an input changes, it is because of a clock edge. And we discussed kind of that the only exception to this rule is when signals are coming from the outside world. Okay, and generally my advice is, unless you're very comfortable with mealy, stick with Moore. I am not comfortable with mealy, so I have a bias for Moore. Okay, but there may be problem specifications which require mealy. Okay, I could have given this problem where basically said as soon as this guy goes 1, you have to go 1 out here, then that would force your hand. Okay, so, but if you have freedom of doing it, detecting, like detect the pattern apple or these kind of things, there I did not say which clock cycle, so you could kind of do it.
So, with regards to like efficiency, is it with respect to like the minimum amount of states, or is there any criteria?
Yeah, see, ultimately the only criterion that matters is how much silicon. Okay, what area would it take on my chip? Nothing else matters. The problem is there is no one-to-one mapping from your high-level design to how much area it will take. Okay, so what the design tools do is they give you estimates. Okay, but I mean intuitively, so the thing is, obviously a flip-flop is a lot more expensive than a gate. Okay, so if I can save a flip-flop, worthwhile. Okay, on the other hand, wires also take a lot of space on silicon. So if I have a very messy design, that can cause a blow up in areas. It's a hard question to answer. Okay, but there are good algorithms which come up with estimates of the cost. Question at the very back.
So you're saying, so we had outside input, so that like, if you have outside input, you're going to need.
So I think there are two conditions under which, okay, there's one condition under which you are forced to use mealy, which is I specifically tell you that your output has to change. So if this problem were to modify to say output is equal to 1 if the input was 1 during the current clock cycle and the one before that. So in this example, if I had asked you that the output would have been 1 and 1 here, then you know it has to be mealy. There is no other way I can implement this thing. Okay. So and likewise, since I wrote it this way, it actually forced the way I sort of the problem was given. It forced you towards more. Okay. But in some problems, I do not specify precisely which clock cycle the action is happening. I forgot whether for the Apple and Google problem I had done it or not. Okay, whether I had said that it should happen after the clock cycle or not. I think I might have. I'll kind of look it up. Usually, I was very careful in that problem to kind of specify what clock tick things are happening. So it's very possible that mealy may not be a solution there actually. Okay, because so it depends on the problem statement. You'll have to look at it very carefully. Yeah. And by the way, sometimes what you can do is if you're really super comfortable with mealy, you do a mealy and then you delay the output by putting a register at the output. So those are called registered mealy machines. Okay, I'll continue with him and then continue. Yeah.
And then for this one you just explained, it seems like you're so the no, I'll go back. The drawing is on the right.
This.
Yeah. So the top is the clock. The second one is the input.
Yeah. So clock, input, output.
Right.
Okay.
It looks like your input is happening right exactly at the clock edge.
It's happening as a result of the clock edge.
So it happens after.
Yeah, teeny bit after,
Okay.
right? So that is the propagation delay of the flip flop. Okay. Okay, your question.
So more machine would always have like a one clock delay and output.
Yeah, so the effect, if my input changed on clock number I, the earliest the machine can do something to the output is the next clock tick. Right? So if clock tick number I caused a change in an input, then the machine's output can react to it only at the next clock tick. Make sense? Whereas mealy can react immediately. Okay, so you can go through the kind of the whole out here that, so the idea is we draw the state machine. This is the same as what I have drawn. Then you convert that state machine into this kind of a diagram, which is a symbolic truth table. So I have not said, I've just given labels A, B, C to the states because I have not assigned a pattern. One of the freedom you have as a designer is assigning bit patterns to the states. And as we saw that we could assign bit patterns to state multiple ways. What were the two common ways we discussed? One hot coding and compact coding, right? I mean, okay. So in this case, if I were to do one hot coding, how many bits would I need? 3. And if I do compact coding, I get away with 2. Okay. So let's see what we have done out here. We did compact coding. So we assigned A 0 0, B 0 1, C 1 0, made 1 1, don't care. But I have a lot of freedom. I could have assigned A 1 1 and B something else, and so, right. I mean, so there's a lot of freedom out. And again, going back to kind of this has implication for cost. Maybe one assignment results in a simpler design than the other, and therefore cheaper design. But in any case, we try this and then we do the next state. And for the next state, we consider both the cases. Input is 0, input is 1. We kind of write them down. There's a bunch of don't cares, and then we write down the output. So what we really have is a combinational logic which we have to design, which takes 3 inputs, the 2 bits of state and the real input, and produces 3 outputs, the 2 next state and the real output. So I have to design 3 functions. In a homework setting, you can make use of Logism. In an exam setting, you have to do it by hand. Okay, and in a professional setting, you will use tools like EOSS and all. Okay, to do the task for you. Okay, so you make up the K-maps if you wish, or if you are really good at it, you can perhaps even write the equations straight away looking at this stuff. Okay. K-maps for the output, you make the circuit, and we are done. And you draw the timing diagram to verify it. That's the typical pathway. Of course, this kind of approach, this kind of pure hand approach is something that I cannot really offer very complicated problems with, right? I mean, more so in an exam setting. So you should be prepared to do these things, but these problems intrinsically are going to be simpler, okay? And they essentially correspond to like the problem number 1 and 2, which we had in the homework. So let me pull that up to remind you of what that had looked like. We had these problems. Okay, so basically I'd given a simple state machine and then I asked you to kind of go through the entire pathway both ways with a particular compact coding as well as with a one hot coding. And I'm not going to bore you through this thing, but these are relatively simple kind of stuff. You should be able to do problems of at least this complexity, perhaps a little bit more, but kind of roughly in this ballpark, very small number of states, purely manually in the exam setting.
Yeah, with regards to the first problem, usually that thing is you sort of also probably request it as you like give a description of the system.
Right.
So this applies if there's a functional description, just like say if I was able to say what the output is.
So I think I had sent a posting on Piazza. I did not want you to describe that, oh, this is a state machine with 3 states and I jump from state 1 to state 2 and under this condition and all. That's not what I'm looking for. That's just a description of the structure of the FSM. I wanted you to kind of do the reverse act, okay, which is, I remember someone designed the state machine given some behavioral expectation. I want you to go in the reverse direction. I want to see whether faced with this, you can extract that what was that original high level description of this machine. Okay, now of course, it's kind of like saying I give you a pattern and I say, what is it? And you may see pattern 1 and I may see pattern 2, depends upon where it comes. So there's no single right answer to it. What I had written was this, but there may be other ways of approaching it also. So I said this is a periodic waveform generator. Where A is an enable signal and then B decides what's the duty cycle, period and duty cycle of that periodic waveform. So A equal to 0, output is frozen in 1. A equal to 1, B equal to 0, output has a period of 2 clock cycle, 1 0 1 0 1 0 kind of pattern. And if B is 1, then output has a period of 3 clock cycle of a pattern of 101 101 101 like that. Okay, that's how I thought of it. Now maybe there is some other equivalent high utility kind of description that you could kind of come up with. I think even in the problem that was due today, there was a similar thing like that. So when I'm asking for this kind of a description, I'm really forcing you to. It's kind of like I throw at you assembly code or C program and say, what was the purpose of this application? That's what I'm looking for. Okay, it's not easy, and but try to kind of abstract it away, abstract the details out to kind of move higher. Okay, you were raising your hand for a while, so I'll come to you.
I guess the question I had was like, I remember like the next state logic, but I guess like the one hot actually got like a little complicated. I feel like
one hot usually has the simplest logic.
I guess it's for I guess I recall like it was pretty complicated.
Okay, so unfortunately, complication is also in the eye of the beholder. So. But usually, I mean, at least for modestly complicated problems, for very trivial problems, it could be different. Okay, so in this case, I certainly grant you that going from that one hot may actually be harder. Okay, but if you recall when we had done the traffic light stuff and all, the compact coding was murderously complicated logic, whereas one hot code was you can look at the state machine and write it out. Okay. But for very simple examples, that's certainly true. This happens to be one. It's very, very trivial. Okay. There was another version out here. What does it do? I kind of thought of this thing. Okay. It's a lock with 2 buttons, A and B. The lock gets locked if A and B are pressed in sequence in successive cycles or are pressed together. And then the lock remains locked as long as A and B are both pressed. Otherwise, it goes back to being unlocked. Now, again, there may be other ways of looking at it. Yeah. Using what? Yeah, you can. That's fine. Yeah, that's fine. Look, we are not out to. This is not a gotcha thing. So yeah, those variances are fine. I'm looking for that. Did you get the concept? Okay. Yeah, a lot of you ask questions where, like, you're worried about inconsequential stuff. I think in the process, you risk missing the big picture or the important aspects. So don't worry too much about the dotting the i's and all. Okay, so yeah, you draw the flip flop. That's fine. It doesn't change the fact. Okay, where is it?
Aren't you supposed to draw the flip flop?
I did not. Yeah, let's see what did the problem ask for. Okay, maybe I flunked it. Yeah, implementing the FSM. Okay, you do. I did not. Okay, so I'm now going to penalize myself, but okay. But again, look, I mean, facing a situation like this, we are is that's it's this combinational part which is the important thing, and did you get the number of state bits right and the way they were connected? So yeah. Questions on this side? No? Oh, more? Okay.
Okay. So when you go to the table that you use for the
Which one?
like the next state and the output.
Oh, from on the slides?
For the
Oh, for the homework.
yeah.
Oh,
Like for the more machine, like okay, the output depends on the state that you're going to, right?
no. For the more machine, the output depends upon the current state.
So that means okay.
Yeah. So which is why, yeah, I have not drawn it this way out here, but in some other cases, for the next state, we draw it as a function of the input, but we don't draw the output that way. What I mean by that is that, so in this case, the machine is clearly a more machine, right? Because the output is just attached to the states. So a more clearer way of writing this table could have been that the next state, I would have then drawn 4 columns under next state corresponding to the 4 possible combinations of A and B. Okay, whereas output I would have just drawn like this, thus thereby indicating that output is independent of A and B. So let me rephrase. I would have drawn this diagram. I could have drawn this diagram something like the following: that I would have S1 colon 0. That would be my input side. I would have next state 1 colon 0, and I would have 4 combination: AB equal to 0 0, AB equal to 0 1, AB equal to 1 0, and AB equal to 1 1. So I would have drawn next state like that, and then finally I would have it a Q to that. So I could have drawn it that way also.
Is there any situation where the output depends on what your next state is going to be?
No, can't.
It can.
Hmm? Cannot, right? I mean, think about it. You are asking for it to predict the future.
But
We are describing combination logic. All it has access to is what is the situation right now. Right? Now, what you could do, okay, I know where you're headed. You're basically saying, let me unroll this thing. Okay, so I kind of, I know I'm computing the next state, and therefore I could see that what the thing would be in the next state. The problem is your input may have changed by then, right? So it's sort of, I can see that maybe you can derive some formalism which does that, but you have to think through it more carefully because input can change by then. So the part which you don't know is what the inputs would be. So I guess for more you should be able to do it, but not for melee. Yeah, you should be able to predict what the next, because in more you know the output in the next state would only be a function of next state, right? So based upon my current input and next state, I can actually pre-compute the output for the next state. Yeah, you could do that. Yeah, but whether it would be beneficial and all, I don't know. And in any case, it won't be the more machines that we are talking about. So you'll have to account for the fact that now you are computing stuff a cycle in advance. Okay, let's go back to let's design an FSM that has input W and Z. The machine is a sequence detector that produces z equal to 1, then the previous two values were either 0, 0 or 1, 1. So now I have two patterns to detect. So this is like my Apple and Google version of the problem. So again, what is happening out here is that if you see what in effect what I have done is I have drawn the two good sequences. So A0, B0, C is the good sequence, 1, 0, 0 sequence, and ADE is the 1 sequence, and then I have everything else in the middle which is kind of going on, the transitions that are taking place. So very similar, very simplified version of Apple Google problem. Again, you go through the same state. First write down symbolically what your table is going to look like, then assign state, some bit patterns, then come up with the expressions. So one of the things, say that okay, in this case the expressions are turning out to be complicated. Could I do a different state assignment? So we do a different state assignment. I end up with actually a much simpler equation set. So state assignment matters. So one thing you might want to do is to, when kind of faced with something like that, give a little bit of a thought to that by looking at the patterns, that maybe some bit pattern assignment might result in a simpler logic than the other. Okay. 2FSM approach, same problem. Okay, so design exactly the same problem, 0, 0 and 1, 1. So what we can do is I can create two FSMs. One is for detecting 0, 0, the other is for detecting 1, 1, and then I can output their or their outputs. Okay, so this is an example of what I was talking earlier, that I can actually break down the problem into multiple things and then kind of combine them together. So I could create one FSM detects the occurrence of consecutive ones and the other of consecutive zeros, and then we OR them together. Now, the issue out here is that in this case, I'm not designing a single FSM. I'm designing two FSMs and combining them. This is kind of like a multi-threaded software. So depending upon the problem language, this may or may not be acceptable. If I say, show me a FSM, then you have to show me one FSM. Okay, you cannot give me two FSMs and then show. So for example, for the Apple Google problem, it would not have been acceptable to have an Apple detector and a Google detector and then ORing them, because that would not have been one FSM. But in other cases, usually in the more complicated design problems, I don't say anything. Okay, in which case you are free to break the problem into simpler multiple FSMs, whose results you combine in some way. Okay, let's look at, I think I might have given some version of this problem before. Yeah, this is kind of similar to what was there in the current homework. Okay, so a system receives as input a stream of data symbols which can take values from the set A, B, C, D. Assume the symbols arrive on a 2-bit input and that A, B, C, D are represented as 0, 0, 0, 1, 1, 0, and 1, 1 respectively. What the system does is it looks at blocks of 32-bit data symbols and finds the most popular symbol. That is the symbol that occurs the highest number of times. At the first clock edge, after a block of 32-bit symbol is received, the system outputs on a pin the identity of the most popular data symbol, and on a pin F, the number of times that popular symbol occurred. Okay, so like for example, if A was most popular and A occurred, let's say 17 times, then you would output A on some of the bits and you'll output 17 on the other bits. Clearly Z, which is where I'm identity, would be a 2-bit signal, and maximum possible value of F is 31, so F would need to be a 5-bit signal. Okay. What am I saying? Maximum. Yeah. Actually, let me ask you, why do you think I just wrote maximum value is 31, but I need a 5-bit signal? Why did I write that? Kind of a stupidly designed system. So I'm basically saying that the most popular symbol can have the frequency 0 also. So 32 possibilities, and therefore I need 5. But of course, 0 can never occur. So I only have to represent 1 through 32, so I could have always represented them. So this problem is a little bit not very well formed. But anyway, let's go proceed further. For example, if in the first 32 input symbols, the most common symbol was C and it occurred 20 times, then the output in the 33rd clock cycle would be Z equal to C and F equal to 19. Then if the next block of 32, the most common symbol was A and occurred 16 times, and the output in the 65th clock cycle is equal to A and F equal to 15, and so on and so forth. In other clock cycles, we don't care. Okay, how would you approach this problem? So firstly, let's start. Can I do something like this purely with a control FSM and FSM state diagram? Any thoughts? I mean, okay, in theory you can, but I guess in practice, would you be approaching it that way? No, because it kind of screams for, I'm talking about counts and stuff like that, right? Screams a data path, okay? Next question is, then can I do it entirely with data path? Okay, maybe you can, and some of you have realized are very good at or like to think in terms of data paths. You could do that way, and it's also possible that maybe some simple state machine coupled with this thing might do. In this case, looking at the fact that there is not much interaction happening with the outside world, there's no handshake signals and stuff like that. We're just taking inputs, block, process, put them out. It's probably something we can approach just with a data path. Okay. Then the other thing is to find the most popular thing, right? So how would you approach that? How would you sort of what all information do you need to maintain out here? Yeah.
You just have a counter that keeps track of the number of each letter.
Okay, so I could approach it by having a whole bunch of counters, one for each letter, and I increment them, and then I do the max of them, and then get the identity, right? Okay, so that's one approach.
You could also do like pairwise counters, so that if you start at like the center, and if you see an A, then you increment it. If you see a B, you decrement it, and then you could compare the pairs after at the end.
Yeah, okay, interesting. Interesting. Yeah.
Just have a big array, and then if you see a letter, that array.
Yeah, it's the same thing as bunch of counters. Yeah. Any other possibility? No idea is too bad, so just throw them out. How about, okay, yeah, laugh at it, but I have 32 symbols of 2 bits each, so I have a total of 64 bits. I store them as they are coming in, I store them into a gigantic register, and I have a 64-bit input combinational logic. I could, right? Would be a perfectly valid solution.
I was thinking, would it work to take the bits, add them, then take the average, and based on the average, compute what was most frequently observed? If you
say it again.
So you take each 2-bit, and you add them together, and then you divide it by 32. So you get the average of the sum. That should give you
some idea of which
bit appeared more frequently.
So you're saying just keep adding them, and then I'm not so sure. I mean, you can probably get the extreme. Yeah, I don't think that would work very easily.
Why does it ask us to output one less than the actual number? Is that just the way?
Well, so the idea is the following, that okay, because I have 32 symbols, so it's possible that all of them were the same letter. So I can have a frequency of 32, but that would need 5 bits. But I realize that for the most popular symbol, it can never be the case that the frequency is 0. So 0 is never used. So only valid values are 1 through 32. So to save on a bit, we basically do 1 minus. That's what kind of idea is. But I think my problem's description on that part may be a little bit messy out here right now. But kind of you get the idea that I really need only 4 bits for that. Yeah. Any other thoughts? Any other approaches that you would pursue on this one? Yeah.
Maybe these concepts. So if you so you have a flag that you saw. You have 4 flags. If you see only 2, whichever has more than 15 wins. if you have three, if you saw three of them, whichever has more than three, you'll go with three.
Mhm.
And if you have
Well, okay, so let's pursue the counter theory a little bit more, right? I mean, firstly, I don't need 4 counters, or do I? I need to keep track of that 32, right? I mean, so I need to keep track. So I need a counter for the number of cycles, but then I need only 3 for the letters. Okay, that's one approach. Or I can have one for each letter and always add them up to see how many cycles I have done. Okay, so I could approach it either way. I guess the issue out here is, could you do what's the minimum number of stuff you can get away with out here? Okay, do I need all these counters? Okay, I'll let you guys think about it. So yeah, there's a solution approach. I'll hand it out. Okay, yeah. Well. Okay, another concept: sharing resources. So this actually you are encountering in those of you choosing to do the final design assignment. You are facing it there. So oftentimes what happens is the following: I have to do a lot of operation, but I don't give you enough resources to do that. Okay, so in our design homework, I want you to do the multiplication. Multiplication, naively thought of it, is a whole bunch of shift and adds, but I'm giving you only one adder worth of adder, right? I mean, so that means that you have to somehow find a way of using the same adder again and again and again. So if I have to do a whole bunch of operations, a combinational circuit says I'm going to do all of them in one clock cycle in parallel, right? That's in effect what combination logic does. In a single clock cycle, it does something complicated. Whereas sequential says I'm going to do a part of it in one clock cycle, and then a part of it in next clock cycle, and a part of it in next clock cycle, and so on and so forth. So a combinational multiplier, the like of which we have shown in one lecture, had this massive array of adders and all, and that was one gigantic piece of combinational logic. And those of you again who are attempting this problem, you would realize that I can in each clock I can, instead of doing multiplication in one clock cycle, I can do the multiplication in n clock cycle, and in each clock cycle I can basically compute one partial product and keep adding it up. So this tension occurs a lot of times, which is that I may want to do more operations than the hardware which is available. Let's look at this thing, and I want to compute y equal to 0.25x plus 0.5x n minus 1 plus 0.25x n minus 2. So it's basically, here n refers to the clock cycle. So it's basically saying the nth y at the nth clock instant, nth y, not clock cycle, nth y on the output is 1/4 of the nth x plus 1/2 of the previous x plus 1/4 of the x before that. So this kind of thing can occur in, for example, when you are processing, let's say, sensor data or speech data. So what may be happening is that I may have samples coming. These might be my sound samples. And what I'm doing is I'm taking a window of them and then computing a value. And that's what I'm outputting out here. Okay. And then I'm taking another window and then outputting out here. So I'm basically kind of weighing them and combining them. This is called weighted average, and it's usually done for, any idea why would I do some operation like that?
Like DSP, like discrete time DSP. Like,
Yeah, this is a DSP operation, but what is smoothing it out, right? I mean, it's basically taking blocks of samples and replacing them by a weighted average. So it helps to get rid of noise. Okay, so it's a very common operation. It's again, those of your E, these are what are called as low pass filters. Okay, so that's what it is. Anyway, that detail is irrelevant for purposes out here. What if you see out here, for every sample, I need to do 2 addition and I get a bunch of shifts, right? The shifts are easy, they're just wiring. By the way, just as an aside, those one of the Piazza posting said something for the design assignment about division. There is no division in the assignment. There is a divide by 2 to the power 16. That does not require a divider. Okay, just wanted to throw that out as a wiring operation. So we make sure of that. Going back out here, things like 1/2, 1/4 are just fixed amount of shift. So I need 2 adders out here to pull this thing off, right? 2 adders with some little wiring. But what if I just gave you 1 adder? So clearly I can only process a sample every 2 clock cycles now, right? Because that's the best I could do. Because if I'd given you 2 adders, then you could have created a combinational circuit which would have looked something like the following. 1 adder would have taken x, whatever, point xn by 4. The other adder would have taken xn minus 1 times 2. I would have fed this. I would have this adder, and it would have taken xn minus 2 over 4. And this would be my combination circuit, and every clock tick I could have processed and gotten a value of y. But I gave you only one adder. So I can do one of these additions in a clock cycle, but then I need a second clock cycle to reuse the same adder to pull this thing off. So this tension often occurs in hardware, which is that should I do everything in one go in one clock tick and have a massively complicated combinational circuit? And usually that's not very effective. So what happens is you are given some simpler or lower amount of hardware, and then over a sequence of cycles, you have to orchestrate your computation on top of it. And that's basically what we do on a computer when we write software. A computer is nothing but someone said, you didn't have the luxury of designing the hardware, I'm giving you the hardware. This is all you can do with it. And if you want to do something more complicated, do it as a sequence of instructions. I can play the same game when designing any digital system. I don't have to do everything in one clock tick. I can do it as a sequence. So in this particular case, I have a single adder, and then I have to kind of figure things out on somehow getting it to work. So let's see how it might work out. Okay. So again, writing down things, I want to do 0.25 xn plus 0.5 xn minus 1 plus 0.25 xn minus 2. Okay, and have to keep doing it all the time. And now one thing we have realized is I can only compute one every 2 clock cycles. Okay, so that's already it means that I have to somehow make sure that the input, the outside world is not giving me an input every clock cycle. Then I can never keep up with it, right? Okay, so right at this stage, usually there will be some handshake protocol, or maybe just an agreement that the input will come on every odd or every even clock tick. The other thing which will happen is, since I have a single adder and I have to do 2 operations on it, I have to first do this operation, and then I have to take this value and do the other operation, right? So in one clock tick, I'm going to do the first one. In the next clock tick, I'm going to do this one. And that would be my 2 clock tick solution. Meanwhile, I also have to store the current input and the 2 older inputs, right? So I will have some register where I'm storing xn minus 1, and I have another register I'm storing xn minus 2. And these registers should be updated every alternate clock ticks, right? I cannot update them every clock tick. So I have x out here. I have to make sure that these things are updated every clock tick. That almost argues for, hey, what if I had a clock which was half the speed? That can do the trick, but usually I don't let you do that, so you have to figure out how to make that happen. So you have to arrange that these 2 registers update on alternate clock ticks. Okay, then what will happen is I'm going to take one of this, I'm going to feed them out here. I'm going to get a result. And the next clock tick, I have to use that result. So that basically argues that I need multiplexers out here. Because for the 2 adders, I am needing, I need different pairs of inputs at 2 times. And meanwhile, I also need to store this temporary result someplace. So I have one clock tick, I'm going to do the first addition, store the result someplace, and then reuse this thing for the next clock tick. Now, do I need, one possibility is I can store it into a separate register, but there's another, I can do better. could I overwrite one of these existing registers? If I were to add, let's say, xn and x minus 1, then I no longer need, xn is sitting right at the input, so there's no register for it. But once I have added xn minus 1, well, xn minus 1 I still need for the next clock cycle, but xn minus 2 I don't need. So my better strategy might be I first add these two guys actually. Overwrite xn minus 2 and then use that to add this new one, right? So I'll basically need to arrange that all possible inputs can be connected to the right sources. I have three sources of data, x, xn minus 1, xn minus 2, and I'll have to arrange for these multiplexers to be rightly done. So I will probably need a simple FSM controlling these multiplexers, okay? And then cycle through things. So as you are approaching kind of this design assignment, if you are, think along these lines that I've given you a single adder, you have to do a more complicated multiplication out here. But this is an example. Try to work through this example on your own on how would you create the state machine which will sequence things. And all that is happening is there's something is happening in the even clock cycle and something else is happening in the odd cycle. Okay, and you just have to come up with those two patterns.
So we're allowed to use one adder, but can we use a counter, or is it either an adder or a counter?
It's just counter is nothing but an adder in that regard, at least the type of counter which increments. Yeah. So in fact, you in this problem again, so you're not allowed to use any counter. And also, if you think about it, all that's happening is this logic I'm going to use in one way in every even clock cycle, and a different way every odd clock cycle. Think about that pattern basically. So we are past the time. So I just want to poll. Do you guys want another review session? Yes, yes, yes. Okay. So it's going to be Friday at 6. I'm going to send out the details. Huh? I will record it. Yeah, I'll record it. Sure.
I have a question about time.